Hello, calculus students. Today we'll be doing solids of revolution again, but this time using a method known as the shell method. We'll be revolving this region that's shaded around that vertical axis to create a solid. In this particular case, it's much easier to slice through this with vertical slices because these vertical slices all the way across, it's always the same function that's the top and the same function that's the bottom all the way across. All right, if you try to do this with horizontal slices, you have some problems. Slicing through here is a curve intersecting with itself. We got problems of intersection. It's going to be a mess to try to slice through this horizontally. However, when you take a vertical slice and you revolve this around a vertical axis, it's not going to make a washer or a disc. It's going to make something called a shell. Whenever you're slicing through a region in a way that's parallel to the axis of revolution, then we're going to do a whole bunch of shells and then add up the volumes of all the shells to get the volume of the entire solid. Okay, so in our work here, let's indicate the presence of a vertical strip through this region. And when it revolves around this axis of revolution, you should be imagining something like this. You can create this shell. Let me move this down and discuss some of the dimensions of this that are going to be relevant to us. Now imagine that you took this shell and you unrolled it. Like you cut it right here, for example, and then unrolled it into a rectangle with a little bit of thickness. If we can find the volume of this rectangle, then that will be corresponding to the volume of this shell. And then we just have to add up all the shells that we would make as we do different vertical slices right through this region. Well, to find the volume of this box, we need to know its thickness. So one dimension will be dx, right? That's the thickness of the strip. Another dimension we need to know is how high the shell is. So I'm going to use an h to represent the height of the shell, and that's going to be the... Then we need to know how long this rectangle is. And in order to do that, we got to figure out the circumference of the circle. If you were to look at this shell straight down at it, you would see a circle, and the circumference of that circle would be the length of this rectangle here. So we need to know the radius of this shell. That's going to be important. And if you know the radius of that shell, then you can do the formula for circumference, which is pi times diameter. And diameter is twice the radius. So 2 times the radius times pi. So the volume of the shell is just going to be length times width times thickness, 2 pi r h dx, which means that the volume of the entire solid will be found by adding up all the volumes of the shells, 2 pi r h dx. And then we say, well, where does the first strip start? Well, it happens at x equals a. Where's the last strip? We'll say it happens at x equals b. And we put those as limits of integration. Also, since we're doing vertical strips in this drawing, the width of each strip is the dx. We need the r and the h in this picture to be functions of x, because different shells will have different h's and different r's. As x varies from a to b, you're going to get a different r and a different h along the way. I'm going to come down here and emphasize that by saying that the r has to be some sort of function of x times an h, which has to be some sort of function of x, and then times the dx. And this is our formula that's known as using the shell method for finding the volume of a solid of revolution. If this picture were on its side, rotated 90 degrees, then everything here would just be in terms of y. You'd be integrating between two y coordinates, two horizontal lines, and then you would still be doing 2 pi r h dy, and the r and the h you would want to be functions of y. Okay, let's go ahead and apply this in our first example. You'll notice that this is the same region we did in our last lecture. The only difference is, in our last lecture, I revolved this region around horizontal lines, but in this lecture, I'm going to revolve this region around vertical lines, in particular revolving around x equals 0, which is the y-axis. We're also going to be doing vertical strips, so I'm going to draw one such example of a vertical strip. And then when I revolve that vertical strip around a vertical axis of revolution, you're going to wind up with the image of a shell. And we want to know the radius of the shell and then also the height of the shell. Well, in this picture up here, the radius, if you were to focus on, say, this point on the curve, how far is that point from the y-axis? Well, that's just the x-coordinate. That's also going to be the radius in our, and then the height of that shell, well, that's just the y-coordinate. However, we want everything to be in terms of x, right? Because the thickness is the dx. We're doing vertical strips. So I need to express this y in terms of x, and I use this to do that. Y is equal to 2 plus cosine of x. And now I'm in a position to write down an integral that's going to give me the volume of this solid. So the volume will be an integral from the first strip happens when x is 0. The last strip will be over here at x equals 2. And then we're going to do every strip in between. So we're going to integrate from x equals 0 to x equals 2. And we do 2 pi r h dx. So in this case, that means we're going to be doing an integral from 0 to 2 pi. The radius of revolution is just x. So the height is the y-coordinate, which is 2 plus cosine of x, and then dx, and then that's it. And this is our integral. Now to do this one by hand, I would recommend that you factor the 2 pi out to the front, but this x you want to distribute, and integrating 2x is easy, but then to integrate x times cosine of x, you're going to want to use integration by parts, the table method. But I'm not going to spend any time doing integration by hand for this video. If you go to Desmos and calculate this, you will get about 27.661, and then of course this is a volume, so it should be a cubic unit. Okay, so there's our first example. Let's do the same region, but this time we're going to revolve around x equals 5. X equals 5 is way over here this time. It's still to our advantage to do vertical strips, so I'll draw an example of a vertical strip. And because our vertical strip is parallel to our vertical axis of revolution, this will make the shape of a shell when I revolve it. Now, all we have to do is figure out how long the strip is, because that's going to be the height of the shell. And then how far is that strip from the axis of revolution is going to be the radius. When you actually revolve this particular strip across this axis, it's going to make a pretty wide-looking shell, so something like this. Well, we've already established that this length right here is given by the x-coordinate. And we also know that from the y-axis to the axis of revolution is 5 units, r. That's going to be the total length 5 minus that amount x. And then the height is going to be the y-coordinate again, which we're going to use this 2 plus cosine of x. All right, so the only thing that really changed here was our formula for the r. So we're still going to do the volume is equal to an integral from 0 to 2 pi times r, which is 5 minus x, times h, which is the height is the y-coordinate, which is 2 plus cosine of x, and then times dx. You wind up getting, in this case, 126.569 cubic units. Okay, let's do the same region, but revolve around a vertical line that's left of the region, but not adjoining it. So we're going to revolve around this line this time, x equals -1. Still want to draw an arbitrary vertical strip over here. Recognize that, again, shells will be produced when I revolve a vertical strip around a vertical axis of revolution. So when I realize I'm using the shell method, I just need to know how tall the vertical strip is. We'll call that the h. And then how far that vertical strip is from the axis of revolution. That's the r. Well, if you were to focus on this point on the curve, the top of the strip, how far is that from the y-axis is given by the x-coordinate. And then there's an extra gap of 1 that we have to cover. So you can see that r will be the x and then add 1 to that. Also remember that you could think of this vertical strip being at location x, and so when you want to figure out how far apart two vertical lines are, you do the right one, which is x, minus the left one, which is -1, right? And that also confirms that you get this x plus 1 is that distance. And the h is still the y-coordinate of that point, and which is still given by this 2 plus cosine of x. All right, so in this case here, our volume is going to be an integral from, again, the shaded region starts at x equals 0 and ends at x equals 2. That's not changing. 2 pi times the radius, which is x plus 1, times the height, which is 2 plus cosine of x, dx. This one gives you about 58.507. Let's do the same example we just did last. So we're still revolving around x equals -1. But this time we have a second function that's going to define the bottom edge. The orange is the top curve. The green is this line here. Okay, now I'm going to draw an arbitrary vertical strip through that region. That's going to be the height of the strip. And then this radius is how far the strip is from the axis of revolution. Okay, so once again, like in the last picture, we saw that this strip was x units away from the y-axis. And then there's an extra 1 here. So r is still going to be x plus 1, but h is going to be different. It's going to be the y-coordinate of the orange minus the y-coordinate of the green. Right? So if you wanted to use subscripts, so it's going to be the orange y minus the green y. So the upper function is 2 plus cosine of x minus, and notice that this equation is not presented where y2 is already isolated. Second function solved for y is x halves. Okay, and then once you've correctly come up with expressions for h and r, then you can just go straight to the formula. The volume is going to be the integral from x equals 0 to x equals 2 pi times r is x plus 1, and then times h. H is 2 plus cosine of x minus x halves, and then dx. And then when you calculate this one, you get approximately, use wavy equal signs, 43.847 cubic units. Okay, so this is a familiar shape. A horizontal slice is the best way to go through this region. Vertical slices have the problem of needing to transition right here to a second integral, which we would like to avoid if possible. Where horizontal slices, we can do this in a single integral. So there's an example of a horizontal slice between these two curves. The green one and this one up here, the orange one, and the orange one gave the line, and then the green one, and revolving around y equals 0. Okay, so because our axis of revolution is horizontal, and so is my strip, they are parallel to each other. In other words, when I revolve this strip right here around, it's going to create a shell, which means I need to know the height of the shell. So this shell will be on its side. This is what you need to be able to visualize when you're rotating a horizontal strip around a horizontal axis revolution, and picture that shell. Well, the height of that shell is this length, and we need to know the radius of that shell. So in this picture up here, the radius is how far the strip is from the axis of revolution, and the height is how long the strip is. Let's do the r first. Focus on the green point or the orange point, doesn't matter. Both of those points, how far above the x-axis are they? Well, they're both y units above the x-axis. Also, we're doing horizontal strips. So the region starts at y equals 1, and this last strip will be at y equals 2. And the thickness of each strip will be dy. So everything is going to be in terms of y in this case. I don't need to solve either of these equations and put like the square root, nothing like that. Just leave it y, because I want everything to be in terms of y. However, the h is going to be a different story. The h is going to be found by taking the x-coordinate of the green point and subtracting from it the x-coordinate of the orange point. So I'm going to have to take both of these expressions, 3x is equal to y plus 5, and solve this for x. Remember, I want everything in terms of y, which means you isolate the x. So we get x equals y plus 5 all over 3. And then if I do the green equation, we have y is equal to the square root of x minus 1. I have to solve this for x as well. Y squared is equal to x minus 1, so x is equal to y squared plus 1. So this tells me that the h will be y squared plus 1 minus y plus 5 all over 3. Now, if you want to simplify h, remember this issue of you can split this 3 up under the y and 5, but then also don't forget you're going to have to distribute this negative. So you could write h as the same thing as y squared plus 1 minus y thirds minus 5 thirds. Combine the 1 and the negative 5 thirds. That's going to be 3 thirds minus 5 thirds, so negative 2 thirds. And let's just call that good for h. It'll be y squared minus y thirds minus 2 thirds. And now we're ready to do the volume. Everything's going to be in terms of y. So horizontal strips, the lowest horizontal strip is where the bottom of the shaded region is, so y equals 1. And then the highest strip will be up here at y equals 2. We do 2 pi times the radius. Well, the radius of revolution is just y, times the height. And the height is this y squared minus y thirds minus 2 thirds. Don't forget the dy. The volume is approximately equal to 12.392 cubic units. Let's do the next example. Same region, but a new horizontal line. This time we're revolving around the line y equals 1. We're still going to do horizontal strips. The h is going to be the same thing as it was before, so no difference to the h, because it's still how far apart are the orange and green points. That's still going to be the green x-coordinate minus the orange x-coordinate. Right? It's the same thing that we did up here. And we're going to calculate h the same way, so we're going to get that same result. This time our radius of revolution, though, is changed. How far is the horizontal strip from the horizontal axis of revolution? That's going to be the r. Well, we know the green and the orange points are both y units above the x-axis. And we know that this length here is 1. The axis revolution is 1 unit above the x-axis. Then r is going to have to be the difference of those two. So r should be y minus 1. Okay, so once you have h and r in place, then our volume is going to be the integral from y equals 1 to y equals 2. 2 pi times the radius, which we just determined as y minus 1, and then times the height, dy. And then when you do this in Desmos, you get a volume of about 5.061 cubic units. Let's do the same region again, but this time we're going to revolve around a line that's above. And you'll notice I did not give myself a lot of room to put y equals 5 up here. So this will be not to scale, but let's just say y equals 5 is up here somewhere. We're going to use, once again, horizontal strips. So our h is not going to be any different than it was last time. But now for the radius of revolution, we want to say, well, how far is the strip that I've drawn from the axis of revolution? Okay, so how far is this strip above the x-axis? That length is y. Well, how far is the axis of revolution above the x-axis? That length is 5. Remember, this is not to scale. So r should be the longer length 5 minus that shorter length y. And so let's do our setup. Volume will be an integral from y equals 1 to y equals 2. 2 pi times the radius, which is 5 minus y, times the height, which is y squared minus y thirds minus 2 thirds, and then dy. And this time you get an answer. The volume is going to be about 24.26 cubic units. The last slide is just a summary as far as washers and shells and discs are concerned. I'm going to just use a washer formula. If it's not really a washer, then this r squared just isn't present. You just have pi r squared dx if it's just a disc, right? If there's no hole in the middle. But let's just think more generally. We'll have a washer formula and compare that to a shell formula. Now, the first thing you ever want to decide, given a region, is whatever your region looks like. If it looks obvious to you that you should do vertical strips through there, right? You just do a bunch of vertical strips, then you want to make that decision first, as if you were finding area. Is it easier to find that area with vertical strips, or is it easier to find that area with horizontal strips? Or maybe they're both equally challenging. Often you'll see that one way is easier to do than the other. Of course, there are shapes where you have a function, and a third function, and you're like, okay, if I do vertical strips, I'm going to have to split here and do 2 integrals. It's also the case that if I do horizontal strips, I'm going to have to split right here and do a second integral again. So sometimes there really isn't an advantage to going from horizontal to vertical. They seem equally challenging depending on the region that's being revolved. But make a decision about which way you want to slice through the region, vertically or horizontally. And once you make that decision, we'll begin our flowchart. If you decide that you're going to do everything vertically, then everything will be in terms of x, because your vertical strips will have a width of dx. If the axis of revolution is not vertical though, so it's horizontal. So imagine you're doing a vertical strip like this, and you're revolving it though around a horizontal axis of revolution. When you take this strip and revolve it around there, it's going to make the shape of washers. Hence, our flowchart takes us to washers. Then our formula for washers is integral from a to b pi big R squared minus little r squared dx. And the thing you want to just remember is that these have to be all x coordinates. When I say everything has to be in terms of x, then this r and this r have to be functions of x, or potentially just constants, right? We saw examples where big R was a constant and it wasn't changing as x changed. If you decide you want to slice vertically through the region and you're also doing a vertical axis of revolution, then all of a sudden you've got a vertical strip and you've got a vertical axis of revolution. When they're parallel to each other and you revolve, you're going to be making shells. So then you're going to use the shell formula. But because we did vertical slices, these all still need to be x coordinates. And the r and h also need to be functions of x. Well, what if you decide that you want to do horizontal slices? Then, as you can surmise, everything should just be in terms of y. If you do a horizontal slice and you have a horizontal axis of revolution, in other words, they're parallel, right? If you have a horizontal slice and you have a horizontal axis of revolution, when you revolve that slice around, you're going to be making shells. Horizontal combined with horizontal parallel dictates shells. And then everything has to be in terms of y, so these limits should be y coordinates, and the r and h should be functions of y, potentially constants. And if you're doing horizontal slice through the region and you're doing a vertical axis of revolution, then we've got a horizontal slice but a vertical axis of revolution, and when you revolve a horizontal slice around a vertical axis of revolution, you're going to be making washer shapes. And everything in it should be y coordinates. That should be a y coordinate, that should be a y coordinate, and the big R and the little r may be constant, but if they're not constant, they need to be functions of y. And then, of course, your differentials are y's in these cases. All right, so that's your flowchart, deciding which method to use depending on how you slice through the region. Make this choice here, and then think about what your axis of revolution is, and then let the flowchart take you to the correct formula to go from there. That's all we're going to do regarding how to find the volume of a solid that was obtained by revolving a region around some sort of axis.